Okay, there we go. All right, so welcome back. We had a little bit of a longer break than we would typically experience at this time of year. We have quite a bit of material to catch up on due to said break, so I'm going to do my best to balance moving a little bit quicker through the material. We're still giving ample time for questions and whatnot. I want to get right into lecture set 3 today. So starting on slide 17, which is discussing contingency tables. Just briefly before I do that, I want to mention that lecture set 3 is our probability section of the course. So right now we are learning about the basics of probability. So what I should say is we're learning the definition of what a probability is. And at the same time, we are being introduced to relationships among different events within the same sample space. And we are being introduced to how we can calculate the probabilities of those relationships. So up until this point, we've talked about the fundamental probability, the complement, which is the opposite event of the event of interest. We've talked about the union of two events. Actually, we haven't talked about more than two events. And we've talked about the intersection of two events, and we've talked about the definition of being mutually exclusive. And we've looked at examples of how to list the events that would correspond to these ideas. And we've talked about or looked at examples of computing the probabilities for these ideas. We're going to continue along a similar path in that we're still going to be talking about the relationship between two events in the next parts of lecture set 3. In this particular part of lecture set 3, we are going to be using what is called a contingency table to describe or to visualize the data that we are working with. A contingency table is a table that allows us to visualize two qualitative variables at the same time. So essentially what a contingency table is a table that gives us counts of the particular number of times a certain event or a combination of events has taken place. So for example, in the table on slide 17, we have a total of 833,303 different companies. And what we have counted is the size of those companies. So we have 5,021 small companies, 22,382 medium companies, 805,900 large companies. And we have also counted the healthcare plans that are being provided across the 833,303 companies that we are working with, right? So there, in this case, we have the fee-for-service healthcare plan, which has 341,180 companies subscribed to it. We have this PPO healthcare plan, and we have the HMO healthcare plan. So the values along the axes of the table here and here, those are totals for the two variables of interest, right? So this is totals for size, and these are totals for healthcare plan. All right. And inside the table, what we have are counts of the intersection between the different outcomes for each variable. So for example, this first value here, this is the total number of companies that are both small and have a fee-for-service healthcare plan. Okay, so these values represent intersection between the outcomes of the variables of interest. This value here, for example, is saying that there are 6,491 companies that are of a medium size and subscribe to the PPO. And this value here is saying that there are 233,711 companies that are large and subscribe to the HMO. So what we are going to do is use contingency tables to define 3 different probabilities, one of which we have already seen. The three probabilities are the marginal, the joint, and the conditional. The marginal and the joint probability are very easy to visualize and to calculate. They are simply probabilities of observing the row or column totals. So they are the probabilities of observing the totals that I've highlighted here and here. And the joint probabilities are simply the probability of observing any of the outcome inside the table. So the joint and the marginals are essentially the values on the axis and inside the table divided by the total number of outcomes. The conditional probability is a combination of the joint and the marginal. And what it tells us is the probability of observing a certain outcome given that that something else has had to occur. So a conditional probability is the probability of an event as long or in the space of something else that has to have happened first. And to compute the conditional probability, we require the joint and the marginal. So we're going to go through examples of computing each of these now, and we'll talk about the formal definition of the conditional probability momentarily. Okay. So we're going to define two events for our contingency table. We have event A, the company is small, and we have event B, that the PPO healthcare plan is selected. All right, so A is going to correspond to this row here, and B is going to correspond to this column here. We are asked to compute the probability of A. Okay, so this is the probability that the company is small. So we could think of it like this. So this is going to be little f over capital N. There are 5,021 small companies, and there are 833,303 total companies. So the probability that a company is small is 0.006. Okay. So again, you can see that the marginal computation given the contingency table is quite straightforward. We're just taking the row or the column total of interest and dividing by the overall total number of observations within the experiment. Okay, for probability of B, this will be the probability that we have the PPO plan. This again is going to be little f over N. Okay, so this is going to be 250,018 divided by 833,303. And that is 0.300. All right. I wonder if that slurping sound will be really loud in the video. All right. The next event or the next example is using the same two events. So we have event A, which is the small company, event B, which is PPO healthcare plan. Now what we are asked is, what is the probability of their intersection? So this here, again, whenever we have the ampersand or the word and, those are equivalent. This means intersection. Now, the intersection and the joint, that's the same thing. So really all we're asking here is, what is the probability that I observe a small company that's subscribed to the PPO healthcare plan? So we can compute this in the same way we did the marginal. So we have P of A and B is going to be little f over N. This is going to be a small PPO. So 1,757 divided by 833,303, which is 0.002. All right. Just give it a second. Okay. All right, now what we will do is discuss the conditional probability, which again is simply, which is a combination of the joint and the marginal. Formally, the conditional probability is given in equation 6. This probability is saying to us the probability of event A given, so the line here means given. So this is the probability of event A given event B has to have occurred. So what we are asking is, if you know that event B must take place, what is the probability that you observe event A within the space of event B? So effectively, what the conditional probability is it's a restriction that's placed on the sample space. So we're now only considering a portion of the sample space, and then we are enumerating an outcome within that portion. From a technical standpoint, computing the conditional probability is still very straightforward, because we simply take our joint and we take our marginal and we divide the joint by the marginal. Notice that the joint probability in the numerator, we can write this as P of A and B, or we can write it as P of B and A. Okay, so it doesn't matter which order you do this part in, because those two joints are the same thing. But what does matter is that in the numerator, or in the denominator, we have event B. So with the conditional, it doesn't matter how we write the joint, but we must make sure we use the right denominator. So whatever we condition on is what gets placed in the denominator. For example, if we were to consider the probability of B given A, this would have the same numerator, but we would now be dividing by P of A. Okay. Right here, Alicia. No worries. Okay, so let's take a look at an example. For the same illustrations that we've already been talking about, we want to compute the probability of A given B. Okay, so I'm going to show you how we can do this just by using the formulas, and then I'm going to show you what this means in the context of restricting the sample space. So if we consider the probability of A given B, then we have the probability of A and B over the probability of B. From our previous work, we know that this is going to be 0.002 divided by 0.300, which is 0.007, right? So we calculated the intersection and the marginal in the last two examples. So that's where I'm pulling these values from. Now, we can also show that if we were to use the fraction representation, what's happening here is we have 1757 divided by 833,303 over 250,018 divided by 833,303. Okay, and that gives us 1757 divided by 250,018. Okay. Now, the reason that I wanted to show you this second expression is because you can see what's happening here is that the total is being canceled out. So we're ending up with only this section of the contingency table. So our denominator is now only the total number of PPO companies. And we're considering the probability of getting a small company out of all of the PPOs. So the question, as it is written, is actually saying, what is the probability that you get a small company given the company has to be a PPO? So we're asking, what is the probability of getting a small PPO company, or getting a small company if you are only considering PPO companies? Okay, so this is what the condition is applying. We are now restricting from the total sample space to only the PPO section of the sample space. And we are looking for the small companies that have to be PPO. Any questions? Okay, so we're going to go through another example of enumerating the same outcomes. We're just going to use a different section of the contingency table now to illustrate these events. So these are the same definitions that we had just talked about, the same structure of examples. The only difference is that we're considering a different part of the contingency table. So we're going to let C be the event the company is large. We're going to let D be the event that we have an HMO healthcare plan. We want to start by finding the probability. Okay, I've left myself lots of room. So we want to start by finding the probability of observing C and D. So the probability of C and D is going to be little f over n. So this is a large HMO company. And that gives us 0.280. All right. And then we are asked, what is the probability of C? Okay, so now we're looking for a large company. So this is going to be F over N. So this is going to be 805,904, 900, sorry, divided by 833,303. And that is 0.967. All right, and then in part 3, we're being asked, what is the probability of observing a HMO healthcare plan, a company subscribed to the HMO healthcare plan, given the company must be large? Okay, so we are only considering large companies now, and we want to know the probability that of the large companies, we randomly select one that has the HMO healthcare plan. All right, so this is going to be the probability of D intersects C divided by the probability of C. From our previous work, this is going to be 0.280 divided by 0.967, 0.29.
If you were to not have those first two, and you were to write like how you wrote it originally, like with the fraction, would you have to show that you canceled like out those values in the original one, or could you just simply skip over to the fact that you could simply write oh dear, what were the numbers?
I got it.
2000, yeah.
Yeah.
200.
So technically, if you were to skip and go right to this, okay, this is not, you're going to get the right answer. The only issue here is that technically this count is not the probability. So right now we have a disconnect between these two parts. Okay, so these do not equal one another. So you should have the completed expression here,
Okay.
just because otherwise, because this is the probability. If you don't write this, then it's not the probability, it's only the count. So now we have a disconnect and this line does not equal this line.
Okay, sounds good. Thank you.
All right. Okay. Any other questions? Because the last decimal place is 0. The definition of every probability is little f over n. Every probability calculation that we talk about boils back to the definition of the fundamental probability, which is defined in this course as little f, all the ways the event can occur, divided by capital N, which is the size of the sample space. So in all of these situations, I'm applying the little f over n notation in every case. I'm actually doing this. Even with the joint probability, I'm technically doing it as well, but it's just inside the numerator and denominator separately. Yeah, like that's one of the biggest keys to this section is just trying to get back to that little f over n rule. Because again, like any probability that we talk about or ask you to calculate, at the end, it's always going to be little f divided by capital N. It always boils back to that same fundamental definition. It's just how you get to that definition that can be tricky. Yeah, so Brittany, this question was just asked. That's what I was just talking about with the student that came on the mic.
What I mean is in the way that you've written it out here, you've written it in a long form. So with the part of it being written in long form and then the answer happening, do we need to show that it cancels out in between there?
No, that's
Okay.
fine. You can just go like, you can rate it exactly like it is here if you want to do it that way.
Okay,
Yeah.
thank you.
No worries. Okay, cool. All right, so the next rule that we're going to talk about is the multiplication rule. The multiplication rule is just a rearrangement of the conditional probability rule. So you might remember from 6, we had the probability of A given B is equal to the probability of A and B divided by the probability of B. If we multiply both sides of equation 6 by probability of B, we end up with the probability of A given B times the probability of B. is equal to the, we end up with the probability like this. So if we multiply both sides by P of B, we end up with the probability of B times the probability of A given B is equal to the probability of A intersect B. Right? So equation 7, which is our general multiplication rule for two events, obviously. This is simply a rearrangement of the conditional probability rule. So we're just taking the denominator from equation 6 and removing it, or we're multiplying both sides of that formula by the denominator, and we end up with an expression for the intersection. Now, the idea here is the general multiplication rule would apply when you have one event that changes the size of the sample space for the next event. So for example, suppose that we were to draw 2 cards out of a standard deck, but we don't replace the card. After we draw the first card out of the deck, we have now changed the total number of cards that remain in that deck, right? So there's 52 cards. We're talking about jacks in this case. So just again, we have 4 kings, 4 queens, 4 jacks, and then we have 4 of each ace through 10, right? So 4 aces, 4 twos, 4 threes, 4 fours, 4 fives, 4 sixes, etc. In this example, we're saying, suppose 2 cards are selected from a deck. What is the probability they are both jacks? Okay, so here what we are asking is, what is the probability we get a jack on the first draw? And what is the probability we get a jack on the second draw? So this is jack on first, and this here is jack on second. The key though is that we are not replacing the card, right? So we're taking that first card out and we are leaving it out. So maybe it goes into a player's hand, or maybe we just put it beside the deck, but it's no longer counts in our computation of the probability of the second jack. So that conditionality that we talked about in the previous examples is still being applied to the sample space. We're now restricting the size of that space. So here we're going to have the probability that we draw the first jack, which uses the full deck of cards. And then we're going to have the probability that we draw the second jack, given that first jack has already been taken out. So these are computations when we are not replacing the first event, if you will. Okay, so there's 52 cards in the deck. 4 of them are jacks. So this is going to be 4 over 52. And then we have taken 1 jack out of the deck. So our second probability is going to be 3 over 51. 3 remaining jacks out of 51 remaining cards. And this gives us 0.005. In the second example, it's the same idea, except that we're now working with suits, right? So we have our 52 cards and we have 12 spades, 12 hearts, 12 clubs, 12 diamonds. So it says, suppose 2 cards are selected from a standard deck. What is the probability that one is a spade and one is a heart? All right, so we want probability spade and probability heart. Okay, so this is, let's say, spade first, heart second. Oh yeah, you're right, 13. Sorry, thank you. Okay, so this is the exact same idea. All right, so we're gonna have probability spade multiplied by probability heart given spade. Okay, so the probability that we get a spade is 13 out of 52. Then the probability that we get a heart given we've pulled a spade out is going to be 13 out of 51. Okay. Does that make sense? Any questions? Check that math real quick back. All right. Any questions? All right. No questions. We move on. Okay. All right. The next topic is the topic of statistical independence. Now, this particular definition creates a lot of confusion for students. It's understandable, but it's something that we are going to spend a fair amount of time on to try and make sense of. First, in a general sense, or in general, what does it mean when events are independent? And for the most part, we're only going to consider 2 events, but these definitions extend to multiple events as well. Okay, what does it mean when events are independent? It means they occur at the same time, so they intersect, but they do not affect one another. So where students get confused is they think if an event is independent, it has to be mutually exclusive as well. This is not correct. Okay, can't happen. Mutually exclusive events never intersect. Independent events have to intersect. So that's the first difference, and that is very important. So that's something that you just want to, if you have to, just memorize it. If you can internalize and understand it, that's even better. But mutually exclusive events never intersect. Independent events have to intersect. So those 2 things cannot be the same. All right, so that's the first thing we have to make sense of. Now, the second thing, what does it mean for events to be independent? Again, it means that they have to intersect, but they don't affect each other. They occur at the same time, but they have nothing to do with one another. On slide 26, we have 3 formula. These 3 formula can be used if we know the events are independent. So if from the description of the problem, we can tell that the events are independent, we can use these formula for computation. These formula can also be used to check for independence. So if we have a problem that says, are the events A and B independent? Given the information available to us, we can pick one of these three formulas to check if those events are independent. So equation 8, 9, 10, they are rules for verifying independence, and they are formula we can use for computation if we know the events are independent. So they serve two purposes. All right, examples of independent events. The most classic example, well, one of the more classic examples would be rolling two die at the same time. So we've talked about rolling two die at the same time in this lecture set. We've actually enumerated the sample space for two die being rolled at the same time. When you roll two die at the same time, you are creating or you are conducting an experiment that has two independent outcomes. So whatever shows up on die 1 has nothing to do with what shows up on die 2, but their intersection is used in most board games, right? So Monopoly or Settlers, you consider the summation across the die. But those two die are independent of one another because it doesn't matter what I roll on the first die. It has nothing, it's not going to change what comes on the second die. So they are occurring at the same time, but they have nothing to do with one another. So they are independent. And this is the same if you play like Yahtzee, for example, where you have 5 die or whatever it is. Those 5 die are all independent of one another. They don't have anything to do with each other. Whatever shows up on die 1 has nothing to do with what shows up on die 4, etc. So independence means occurs together, but does not affect one another. Right? Card drawing can also be considered independent if you are replacing the card after the draw. So if we pull one card off of a standard deck, we record what it is, put the card back into the deck and reshuffle, we're now creating a series of independent events. Okay. But if you draw cards and do not replace, those events are no longer independent because you are reducing the size of the sample space every time you draw the card out. Right? Any questions? Skip slide. No. All right. So we're going to start off, or we're going to work through a few different examples now that illustrate the use of the formula both for checking and for computation. We're also going to play a little game of which kind of events are we working with based off of the formulas we've learned so far. The first example, are the events A and B independent if P of A is 0.5, P of B is 0.5, and P of A and B is 0.25? Okay, so this first example is asking us to check for independence. We are given the two marginal probabilities and the intersection. Okay, so we're going to check if P of A times P of B is equal to P of A and B. All right. So this is how we are going to determine independence. Does the left side equal the right side? So we have 0.5 multiplied by 0.5 is equal to 0.25. Okay. We're basically asking a question. Is it true that the left side equals the right side here? Okay, so this is going to be 0.25 equals to 0.25. So that's a yes. Okay. So these events are independent because the left side of this equation equals the right side of this equation. I don't know why I'm writing in red now. Let me switch back. All right. In the second example, we have 2 fair die are rolled simultaneously. Okay, in this illustration, right off the start, we are being told what the experiment is. Okay, so 2 fair die are getting rolled at the same time. So we know that the events, or we know that the first die and the second die are independent of one another. The question then says, what is the probability that the first die shows a 3 and the second die shows either a 2 or a 4? Okay, so if we say A is first die shows 3, and we say B is second die shows 2 or 4. Okay. Since we are defining our events to be, well, we are defining event A to be from die 1 and event B to be from die 2, we now know that we are working with independent events. This means that we can use the formula on the previous slide to perform our calculations. So since we already know the events are independent, we can use those formula from the previous slide to compute the probability of what we're interested in. So we want to know, what is the probability that the first die shows a 3 and, so intersection, the second die shows a 2 or a 4. So we want the probability of A and B. So what is this equal to? All right, well, again, we know A and B are independent. So since A and B are independent, the probability of A and B is equal to P of A times P of B. Okay, so P of A is the probability that a die shows a 3. So this is going to be 1 out of 6. P of B is the probability a die shows a 2 or a 4. So this is going to be 2 out of 6. So their intersection is going to be 236, which is an 18th. So this is 0.05. Okay, the last example is a bit of a mind twister. So this one is saying 1 card is drawn from a standard deck. Just 1. Let A be the event we pull a king or pull a heart, and let B be the event we pull a king. Are A and B statistically independent? Okay, so now we want to check again. So we're drawing 1 card out of a deck. P of A is going to be the event we pull a heart. So this is going to be 13 out of 52, which is a quarter. P of B is the event we pull a king. So this is going to be 4 out of 52, which is a 13th. Okay, we want to check for independence. We have the 2 marginals. So let's compute the intersection, because then we can just use our formula for intersection. Okay, so P of A and B is going to be the event we pull the king of hearts. So this is 1 over 52. Okay, so now we're going to ask, does P of A and B equal P of A times P of B? Okay, well, we have 1 over 52. we have 1 over 52 is equal to 1 over 4 times 1 over 13. This is 1 over 52 equals 1 over 52. So yes. If we draw one card out of a deck, the event that it's a heart and the event that it's a king are actually independent of one another. Again, kind of a mind twister, but we can show it we can show using our formula this is in fact the case. Okay. Okay, we have two exercises here that are based off of what we had just learned. So independence and the multiplication rule. The first one, I don't really like it. I don't like the wording of the question, and I think it's a little bit confusing, to be honest. So I'll go over it quickly here, but just for illustration purposes. So in part one, it says, according to the Opinion Research Corporation, 44% of US women suffer from holiday depression. 50% of US adults are women. What is the probability that a randomly selected US adult is a woman who suffers from depression? Okay, so what's happening in question one is we are asking, what is the probability that we have a woman, a US woman, and she suffers from depression? So this is going to be the probability of depression, given that it's a woman, multiplied by the depression of observing a woman. So in that question, technically the 0.44 is that condition, even though I don't think the wording there is very clear. That's something that I need to address in the future. But just for illustration, that's what that question was getting at. But again, the wording there is pretty tricky. You're not going to see anything that obtuse in the assignment. Okay, we'll move on to the second one though, because that one I think is a bit better. Okay, so in question two, we have, suppose you agree to participate in an ESP experiment and you are asked to randomly select two numbers between 1 and 6. The second number has to be different from the first number. All right, let H be the event the first number is a 3 and K be the event the second number is greater than 4. We want to then calculate the probability of H, the probability of K given H, the probability of H and K, and the probability that both numbers are less than 3. Okay, so we have this ESP experiment. You're asked to randomly select a number between 1 and 6. The probability that you select, or the probability of observing event H, which is the probability that you select a 3, is going to be 1 out of 6, which is 0.167. Okay. In part B, it asks, what is the probability that you select, or what is the probability of K given H So this is the probability you select a number greater than 4, strictly greater than 4, given you selected 3 on your first try. And remember that in this experiment, the second number that you select has to be different from the first number. So you're creating a condition, because in the second case, you can no longer pick 3. So this is going to be the probability of K and H divided by the probability of H. Okay, so in this experiment, on our first attempt, we're going to select a 3, which has a 1 out of 6 chance. On our second attempt, we're going to select a number greater than 4, given that the 3 has already been taken out. So here, we should have that would be confusing. Okay. Okay, so here what we will have is the 1 out of 6 for the probability of selecting H multiplied by the probability that we select a number greater than 4, given that we've already selected the first value, which is going to be 2 out of 5. Okay, so this is our P of H, and this is going to be the P of K. There it is. Yeah. I mean, technically this is given H, which is going to be confusing. So I'm just going to write this as probability number greater than 4 given 3 selected, which is still the same thing. Okay, and then we're going to divide by P of H. Well, actually, you can see how this works out, and this gives us 2 over 5, which is 0.4. Okay, in part C, we are asked for the intersection, I believe. So this is going to be K and H. Just going to check that real quick. Oh, H and yeah. So here we have the probability of H and K. Okay, so this is the probability that I select a 3 on the first try, and then on the second try, I select a number greater than 4, given that I selected the 3. So this is going to be the following. Multiplied by 2/5, which is 0.067. No, in this case, it looks like they would be independent. So if we were to check, using the formulas, we should be able to show that the intersection is equal to the product of the marginals here. Because you can see in the top part, I have P of K and H. Sorry, the question was, so it's not independent. So you can see in the numerator here, I have the probability of K and H. And then what I'm doing is I'm taking the probability of H and I'm probability of H is this and multiplying by the probability of K. K is the event the second number is greater than 4. So K is strictly the event the second number is greater than 4, which means that something had to have happened first. No, actually, you're right. Yeah, so they wouldn't be independent. Yeah, they're not independent. That's true. They shouldn't be anyways, depending on what happened first. Yeah, that one's a bit tricky. Well, we're strictly focused on K and H. P of K times P of H. I don't think we can say for sure they're independent because H is the second event rolled and it depends on what happens on the first attempt. So like how you would compute the probability of H would have different outcomes depending on what the first attempt was. So I think it would be fair to say that they are not in this case, but I think it would be fair to say that they are not. The probability both number, okay, so part D, it says the probability both numbers are less than 3. Okay, so this will be first less than 3 multiplied by the probability the second is less than 3 given the first is less than 3. Okay, so the probability the first number is less than 3 is going to be 2 out of 6 because there's only 2 numbers out of the 6 that are less than 3, which are 1 and 2. So that's a 2 out of 6 chance. The probability the second number is less than 3 is then has to be 1/5 because we on the first attempt we picked one of the numbers less than 3 and then we have reduced the size of the space because we can't pick the same number again. So we have a 2 out of 6 chance of selecting a 1 or a 2, and then depending on which number we select, we then had we have a 1 out of 5 chance of selecting the other number that's less than 3. So that gives us 0.067. Oof, so many questions. Sorry, I know I'm going kind of fast. Any other questions? Sorry, Jessica, if that wasn't the clearest answer. It's a bit tricky, I think. We're using the multiplication rule to compute the probabilities. When we're using the multiplication rule, we have the condition there. And yeah, in this, we would have to check. It's not, I don't think they would be, but I could very well be wrong and embarrass myself on the old tube of you. Sorry, any other questions though? All right, we are going back to our contingency tables now. In this example, we have a contingency table that's actually showing us the joint probabilities rather than the counts. So this table is actually going to be interpreted pretty much in the exact same way as the original contingency table. The only difference here is that we have taken the total size and we've just divided every number in the table by that total size. So instead of having a contingency table of counts, we now have a contingency table of probabilities. Okay, so we've just created a different visualization of the same information. So if we were asked for specific probabilities, we have the marginals and the joints directly, the marginal and the joints are now being displayed and we don't need to compute them. We can just pull them out of the table. Okay, so we are going to use this contingency table to determine if events P1 and C2 are independent of one another. So we are asking if the events are independent. In this case, P1 is the event that the Congress is democratic. So this is going to be our P1. And C2 is the event that the Congress is a representative. So this is going to be our C2. Okay, are P1 and C2 statistically independent? Verify in two ways. Okay, when we ask to verify in two ways, it means pick two out of the three formula that were available to us for checking for independence. Okay, so we have three ways to check for independence. Okay, so the first one is, does the intersection equal the product of the marginals? Okay, so this would be one. The second one would be, does A given B equal P of A? And the third one would just be, does the probability of B given A equal the probability of B? Okay. So we're going to pick two out of these three equations and see if the left side equals the right side. That's the purpose of the question. We want to verify independence. We're just asking for these equations, does left side equal right side? Now, if you verify this for one equation, the other ones will also hold. So these three equations also agree with each other. So there isn't actually any reason to do it with two formula. The only reason that I'm showing you two ways is so that you can see how you would use different rules. But if you are asked to verify independence on an assignment, you only have to do it using one of the three formula, and you would pick the formula based off of the information that you have available to you. Since we are working with a contingency table, we have marginal and joint probabilities directly available to us. So the logical formula to use here would be the first one. Okay, so we're going to start by, okay, so this will be first way. So does P of P1 and C2 equal the probability of P1 times the probability of C2? Okay. Okay, so from our contingency table, the probability of P1 and C2 is 0.374. The probability of P1 is 0.471. The probability of C2 is 0.813. So we have 0.374 is equal to 0.471 multiplied by 0.813. Did I get those? Okay, so 0.374. If we multiply these two probabilities together, we get 0.374 383. Okay, so this does not, the left side does not equal the right side. So we would say not independent. All right. Okay, so again, now that we have shown they are not independent, we know that this is going to be the case for the other formula as well. So this second way of showing that they're not independent, we already know the outcome. This is simply for illustration. You don't have to do it two different ways, just to show you how the formulas would work. All right, so let's say that we use, I don't know, the second formula. It doesn't really matter. So we're asking, does the probability of P1 given C2 equal the probability of P1? Okay, so this is the probability of P1 and C2 divided by the probability of C2 equal the probability of P1. Okay. All right, so P1 and C2 is 0.374 divided by the probability of C2 is 0.813 equal to the probability of P1, 0.471. Okay, so this is 0.460 does not equal 0.471. Okay. Any questions? Independence extends across multiple events. So we have looked at examples where we only have two events occurring at the same time. And these will generally be the types of events that we consider in the class. But it's worth noting that the idea of multiplying the marginals together to find intersection can be extended to as many events as there are in the space, as long as those events are independent. So if we have events A, B, C, D, E, F, G, and all of those events are independent of one another, we can multiply their marginals together to find intersection. Okay, so independence, the definitions extend in terms of intersection across multiple events, more than two events. All right. The last thing I want to do before we move on to counting rules is use the formula that we have discussed so far in the class to determine if the events are mutually exclusive, independent, or neither. In this case, neither would mean dependent events. It would mean dependent events. The purpose of these exercises is to highlight that mutually exclusive does not mean independent. So if the events are mutually exclusive, they cannot be independent because independent requires intersection. If the events are mutually exclusive, if the events are not mutually exclusive, that means that they intersect. If they intersect, they can be either independent or dependent. So again, independence requires intersection. Therefore, two events that are independent cannot be mutually exclusive. These are different things. All right. In exercise 1, it says, Are the events A and B mutually exclusive, independent, or neither? Again, neither in this case would just mean dependent. If P of A is 0.3, P of A or B is 0.65, and P of A and B is 0.15. Okay, so first, right off the bat, we can say since P of A and B does not equal 0, A and B are not mutually exclusive, right? So they have an intersection, so they can't be mutually exclusive. Mutually exclusive means no intersection, right? So that's automatically out. Okay, now we have to check for independence. Okay, so we have to check. In this case, we can use P, A, and B equals P of A times P of B. The reason I'm using this formula is because I have 2 out of the 3 parts that I need. So I have P of A and B, and I have P of A. I just need to figure out what P of B is, and then I can plug it in. Okay, so find P of B. Okay, so we know that the union of 2 events is going to be P of A plus P of B minus the intersection. So we have 0.65 is equal to 0.3 plus the probability of B minus 0.15. Okay, so this gives us P of B is 0.65 minus 0.3 plus 0.15. So that gives us 0.35, 0.5. Oh, good. Gave myself lots of room. What an idiot you are, Brian. All right. Anyways. Okay, so now we can go back to the checking part. So we have 0.15 is equal to 0.3 times 0.5. 0.15 does not equal 0.06, is it? Oh, never mind. Oh, okay, maybe I made it. 0.65 minus 0.3 is 0.35. 0.35 plus 0.15 is 0.5. Okay, so then yes. So these are independent. Okay. In part 2, it says, are the events A and B mutually exclusive, independent, or neither if A given B is 0.65 and the probability of A is 0.35? What do you mean? Why am I multiplying by 0.3? So this P of A is 0.3, P of B is 0.5. I want to take the product of the two. Okay, cool. Okay, so for part B, this is actually a very quick check. So our second conditional rule is P of A given B is equal to P of A. So here we can just write check. Does P of A given B equal P of A? Okay, so we have 0.65 does not equal 0.3. So this would be neither. Right. So that's a quick one. And then for 3, it says, are events A and B mutually exclusive, independent, or neither if P of A and B equals 0? So since P of A and B equals 0, A and B are mutually exclusive, right? Because that's just the definition of being mutually exclusive. When they don't have an intersection, which is the case here, they are mutually exclusive by definition. Any questions? Min, would 2 be considered dependent then? Yes, they would be considered dependent. Kareem, so if the set equals 0, then it's always mutually exclusive. If the intersection between 2 events is the null set, or the probability of the intersection between 2 events is 0, then they are mutually exclusive. But your mutually exclusive applies to relationship between 2 events. So there have to be 2 in the space with no intersection. Yeah, so for example, yes, that's true. If they're dependent, they have to intersect. So if you have a conditional probability, you must also have intersection. The conditional does not exist if there's no intersection. All right, so we still have a few minutes left. I want to go through an illustration of the basic counting rule before we finish today, and then we can finish counting rules Thursday and hopefully take a big chunk out of lecture set 4 on Thursday as well. Okay, so the last part of lecture set 3 is on counting. The idea here is how can we enumerate all of the different outcomes within a sample space if the sample space is really, really big. So we have looked at illustrations so far where we can visualize the sample space fairly easily. But with many probability problems, this won't be the case. So we need to develop techniques to count how large a sample space is if we can't basically make a list of it. So counting rules are tools that allow us to do this. The first counting rule is the basic counting rule. The basic counting rule just says that if you have R different outcomes or R different actions, the total number of possible outcomes within the space of interest is going to be all the way the first action can occur times all the ways the second action can occur times all the ways the third action can occur, etc. Okay, so to illustrate this idea, I'll show you one quick example here. At McEwen, we have to change our passwords fairly often, more often than I would like. The question is, how many different passwords are possible if the first 4 entries must be unique letters, lower or uppercase, and the remaining 5 entries must be unique numbers? Okay, so this is an application of basic counting. We have 9 total actions. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we want to know how many different outcomes are possible given these 9 different possible actions. Okay, so the first action is choosing a letter, lower or uppercase. There's 26 letters in the alphabet. If you consider cases, we now have 26 lowercase, 26 uppercase. That gives us 52 options. We then have 51 options, 50, 49, because we have to have a unique letter in the first 4 slots. For the numbers, we would have 10 options for the first number because we're including 0, 9, 8, 7, 6. Okay. So this gives us 481,376,000 different passwords under this particular combination. All right, I'll pick up here next time and go over this again, and we'll look at some more examples. But again, the last part of the lecture set is counting rules, and we'll start lecture set 4 on Thursday after we finish the counting rules. So have a good couple of days, and I'll post the video for this as always, and I will talk to whoever wants to come on Thursday. Okay, so see you then.